I will check whether the quality is good during the break. Okay. So today we talk about connections issue. Okay. So last time we talked about how to establish the connection, how to tear down connections. We understand that there is a time wait. Okay. Whenever you control C or accidentally stop any connections. Stop the server while you have connections. Then you take a time wait, and before it, we will have a three-way handshake. Okay, so let me ask a quick question after you have finished assignment 1, right? The quick question is, previous sets of slides we talk about three-way handshake, right? It usually starts with the client connect to the server. Should the client always send the first message? Application message. So for three-way handshake, you know that it's client start the first message, start the first TCP packet, right? It start the saying and then saying act and then act, okay? Then the fourth message should be the application message, right? Who started? Is it always the client? Can it be the server? Understand what I mean? You have a client, right? You have implement your application. And our application is like that. When you start the connection, it's always the client say the hello, right? Do you remember? So my question is, I just changed the game. I don't want to have the client start the first application message. I want the server. Is it possible?
Yes.
Yes, right? How many of you think that no? Okay, so everybody think that is yes, good. Okay, so that means that while you have a connection established, there is none of the business of TCP. Okay, the TCP start with the client, but it's never say that the application protocol always start with the client. Okay, you can start with either side or either side both the same message together. There's no problem. Okay, now that means that the connection problem, what we're talking about is not directional. Okay, I'm going to talk about something that not about directions, but about throughput, about how to control the connection status while you keep, let's say that I want to dump a 1 gigabit of data, 1 gigabyte of data from one side to another. How can the other side, okay, get all the 1 gigabyte without any packet loss, or not without, but detect any packet loss? Or you think that, oh, I'm very busy, I'm the receiver, I'm using modem, okay, very, very slow. So how can I control the rate, okay, of the sender side? The sender side don't send too much data, I'm full. Okay, so this is what we call the flow control. So I basically give you 3 issues. One issue is about flow control, and another issue is packet loss. Some increase the complexity things about the packet loss, and the last one is partition control. Now let's talk about the flow control and advertisement window, or advertising window. I love to call it advertisement window. Okay, so what is the meaning of advertisement window? Okay, it's not a Windows 7 advertisement. Okay, it is something really on the packet. Okay, so the meaning of flow control. What is the meaning of flow control? Let's look at the red words that I highlight. Okay, it's synchronizing the speed of the end host. Okay, so this is the greatest summary I can find. Okay, it's synchronized. So what is the meaning of synchronized? You are using let's say 1 gigabit LAN card, okay, 1 gigabit of network card with 1 gigabit of HKBN, okay, wire, okay. I am using iCable sucks, okay. You already know, right? iCable sucks. You don't know? No one knows? Very slow, huh? So let's say we connect together. One is iCable, one is HKBN, okay. One is faster than another. Okay, so how do we synchronize it? Okay, and the way to synchronize it is very natural. How the natural things goes on is you can choose to advertise something inside the TCP packet. Okay, the advertisement says, "Slow down, I'm very busy." Okay, just to tell the other side, slow down. Okay, or in the other way around. Okay, I'm sending from a slow connection. Let's say that. COHK is very fast, okay, and another school, okay, HKU is slow, let's say, okay. CHK is faster than HKU. So CHK pumping data to HKU, then we have the first message. How about HKU pump message to CHK, right? So CHK may advertise another thing. What is that? Come and abuse me. Yeah, I'm very I'm big bandwidth. Okay, I have a what we call a thick fat pipe. Okay, a large pipe here. Come and abuse me. Okay, we can advertise either one of the message. Okay, but you know, you never find such a test message in a TCP packet. Okay, we will quantize it and change it into numbers. Okay, using numbers to represent whether I welcome new data or not welcome new data. Okay, so remember there is a slight difference between that advertisement window and the sliding window protocol. Okay, the sliding window protocol, we have the go back n or set to repeat still. Remember, we have the number called n. Okay, we call it the sliding window width. Remember the sliding window width, and that width is actually hard code in our previous protocol. It's hard code, it's protocol, and it's called sliding window. And in the TCP, we change it a bit. Okay, we change it a bit into a window value that will pack. I don't necessarily pack, but written in a TCP header. Okay, which is not hard code. Is it can be changed, it can be updated. Okay, and so I would say that it's adjustable. Okay, and where can you find it? It is in the window field of TCP header. Okay, so it is a number, and how big it is? 16 bits. Okay, it's only a 16-bit value to represent a so-called window size. So let's take a look at what happened during the three-way handshake. So three-way handshake is actually exchanging window data. Okay, what is the meaning of window data? Okay, it will exchange at least two things. Okay, there will be more. Okay, in new protocol, but at least there are two important things. The first guy is what we call the maximum segment size. Okay, what is that? Okay, it is a field to tell the other side that, hey, don't send a big packet to me. Okay, let's say I'm using a very cheap, I don't know how cheap it is, but it can only accommodate 100 bytes, okay, per packet. Okay, then how to tell the other side that, oh, I'm using that cheap wire, okay, is inside the three-way handshake. Okay, so the three-way handshake, this is the first sync packet, and this is the second sync add packet. Basically, they are really doing handshake like exchanging the name cards. And their name cards, inside the name cards, they state two things, not their names. Their maximum segment size, okay, how big I can tolerate for every packet, as well as what we call the window scaling option. Later on, I will show what it is. Okay, of course, not just the MSS and window options, but also the sequence number that previously you already know. Okay, so remember this in the same, there's a string add. Okay, let's say in our example, I fixed this to be a string number 1460. Okay, 1460. So what is that? Later on, I will calculate the value y is 1460. Then I imagine that we have a very strange wire that can only accommodate 1000 bytes. Okay, so when we try to exchange the data, the real data, the application data, okay, basically there is a thing happening in the lower side. Okay, last time I don't know whether you have take a very close look at the Wireshark capture that I shared last Wednesday. Okay, in the last Wednesday, the Wireshark capture is actually sending stream of data, and the data is being chopped down into a several width. Okay, in several width, and some is big, some is small. Okay, so how to determine the width? Okay, the width is basically determined by the MSS, maximum segment size. Now here, let's take a look here. Okay, so let's say my MSS is 1000, maximum segment size is 1000, and your write call, your system call write. Okay, you open a socket, connect. After connect, you call write, and in the write buffer, you hard code that write length is 3900. So what will happen? In a lower layer, the lower layer will be not having one header, TCP header, and say that, oh, I have a 3900 application data. No, it's being chopped off. Okay, and being chopped off by 1, 2, 3, 4, 4 guys. Okay, so why we have these 4 guys? Okay, so there is something that related to the application, underlying data link layer. Can I find the thing here? Okay, so wait a moment. MTU. MTU? Ah, okay. So let's. How can I show something that you understand? Did you know? I only know how to use command. Okay. MTU. Okay. 哇，唔知，唔係話股票。So happen we have that code. Okay, it's called a maximum transmission unit. Okay, it is a thing related to the wire. Okay, Wi-Fi has its own limit. LAN, the internet has its own limit. Whether you are this version of Wi-Fi or another version of Wi-Fi will change a bit. Okay, let's say I should find a table here. There is a table. No, what? No, yeah, here. Is it? Oh yeah, Ethernet. This is the length, and different version of Ethernet will change the MTU a bit. Okay, so this is about the underlying layer. Okay, so of course Ethernet can grow up to 9K. Okay, we call it jumbo frames. Okay, so this MSS is basically to have a tailor-made width. Okay, for the underlying layer. Okay, and that's why the TCP packet, when you say that in the right system call, you say that at 3900 is being chopped off, and every time you chop off, the maximum segment size determine the data length is 1000. Okay, it is determined by it during the three-way handshake, and the three-way handshake, after it will send in the data, application data. So every application data will have the header. Okay, the sequence number, so on and so forth. Okay, so this is why we have a MSS and why we have to exchange it when we have the three-way handshake. Because the three-way handshake is before any exchange of application data, right? It's carry no data, only carry the TCP header. Okay, so that's why in the TCP header is use the TCP option to tell the other side that, hey, my MSS is this guy, and my SMS is also this guy. Okay, now ask you a question. It's very natural questions. Okay, so you are in the two end holes. Okay, let's say the two end holes is very close together. Okay, this is a must. Okay, it's very close together. Now your network card can support MSS of 1460. That means the maximum segment size of the medium 1460. And on the other side, okay, let's say your neighbor. Okay, your neighbor sitting beside you only can take 1000. Okay, so no problem for this guy. Okay, this guy always sending a packet of segment size of 1000. How about this guy? Can this guy send any message of, let's say, 1460? Why not? Right, the other side cannot take it. Okay? Right, this is even more horrible. IP fragment later on, no. This year we put it in the network layer. In the network layer, we talk about IP fragment. IP fragment is not a good thing. Okay? Imagine you lost one guy, what would happen? Sayonara. Yeah. Okay. Yeah. So this is some encryption between here and me. Okay. So go back. So here it means that we don't want to have such a case that this guy sending 1460 and the other guy, because of the medium, cannot take that big size. We will have trouble. So that's why in the beginning of the connection we exchange it, and both ends will agree on the smaller value. Okay, both sides will agree on small value. Now, after the agreement of this maximum segment size, then we will agree on another size matter. So what is the size matter? Really matters. Okay, so what is that? It's called windows. Previously, I just very lousy say that, oh, the window is to control some data transfer. Now, what exactly window is controlling? Whenever you send a packet out, okay, there is a window field. Okay, let me open up the header again. header field. Yeah, I close it. Okay. Chinook's previous set. Okay. Oh, where are you? Windows. Yeah, here. Window field. Okay, we have the window field here. Okay, every time you send, no matter it's in the three-way handshake, after the three-way handshake, or even in the four-way handshake, this field is always there. Now I will go to tell you what exactly this field is about. Okay, this field is about this guy, the receive buffer. Still remember, we have two buffers. One should create a socket. The two buffer will be created. One is called send buffer. One is called receive buffer. Now, do you need to advertise the size of a send buffer? No. You don't need to tell the other side that how much I can send. The send buffer is to tell your application. It's a buffer between the kernel and the application, right? When the send buffer is full, you tell the application that, hey, stop, by blocking the application. Now, how about the other way? Another way is about the receive buffer. The receive buffer is to receive data from the other host. Now, when the other host keep pumping data in, and your buffer is not big enough, what will happen? Segmentation fault? No. Okay. Packet loss? Maybe. Okay. So when this happens, I'm full. How can I tell the other side that I'm full? Now, before I will tell the other side I'm full, we introduce another way of control by not telling them I'm full. But before the whole connections can establish during the three-way handshake, we advertise how big I am. Right? It's very natural, right? I'm telling you that, oh, I only have this big bucket, okay? Now, another side, I only have a small bucket, okay? Remember, I'm that small. Now, we will exchange the buffer size in the window field. Okay, 1 and 2, they may vary, so I just type some random numbers, okay? I just type in random numbers here to represent the send buffer, receive buffer, okay? Now, that means what? That means when another side keep pumping data in to another side, let's say the client send want to upload a file to the server, it will respect this field. Will it respect the field? It knows that this guy have a 5792, and it will only send at most 5792 packets of data. Okay? So this is what we call a buffer, and you know that by looking at this diagram, both sides buffer may vary. They are not the same. They just try to exchange the information. But there's one problem. Okay, the one problem is the window size itself is only 2 bytes, 16 bits. Okay, so what's the problem? The problem is, what is the maximum number that you can use two bytes to represent? 2 to the power 16 minus 1. So what is the number? 65535. Now, what is the meaning of this 65535? It means this buffer size. Okay, now let's do a very simple calculation. So what is the calculation? I told you that the MTU concept here. Now we use this infinite with 1,500 to do a simple calculation. So what I'm going to tell you is 1500. Okay. Oh, sorry. I should type a 65535. Okay. Divide by 1500. Okay. So it's 43 something packets. Okay. So with the network card, okay, you send 43 packets at once, then the other side will get full. Do you believe that the internet will really work in that way? 43, not 43 billion or million, okay? Look at my previous capture. It's more than 43 packets, okay? So this is a big problem, right? When I really want to try to boost the throughput of the TCP, I really want to expand this, okay? Now the problem is, can I expand this buffer? Yes. The buffer is just a kernel space memory, okay? You want to expand it, go ahead. But you have certain limit. The limit is the window field. The window field only have 16 bits, okay? So how can we expand this? Can we have a 6-way handshakes, okay? You send two two three-way handshake, double the size, okay, two 16-bit, and put it together, 32-bit, okay. No, we are not going to do that, okay. Yeah, not going to 6-way, but still 3-way, but we scale it up. What is the meaning of scale it up? In the TCP option, not just exchanging the MSS, but this is just like I would say the patching the bug, okay. In Cantonese 保爛衫 okay. Yes, we are broken protocol, so we patch it. Now, how to patch it? Let's look at what will go on after the first two packets of the three-way handshake. The three-way handshake, first of all, again exchange the size here. Look at here, I exchange the size, but I exchange one more data called scaling option. Let's say the scaling option is 4, it's called 33. So what is it? It means later on, I will send a smaller number. But you remember, whenever I send to you, okay, I mean the scaling option is 4, so this is divided by 4. Okay? So I look at many captures. Most of the capture will use a scaling option of 32. Okay, most of it. So that means that at least you shift by 5 bits. Okay, it's 5 bits. Okay, shift the bits by 5 bits, or you have a 6. Let me do the modification. Now previous is maybe I make it here times 32. So that means that your buffer now can go beyond at least 2 megabytes. Quite close to 2 megabytes. Okay, so very good, huh? So this is the way how we boost the performance. Okay, to let the buffer can grow no matter what is the case. Okay, later on you will see it. I will look at the capture again. You can look at the window field. The window field is very big. Okay. So this is a 6655 or 35 problem. Okay. So any question about this? No? Okay, so we look at how we use the windows. Okay, now remember this window now is become the go back end, dead end. Remember dead end control the throughput. Now we really don't want it to be as small as possible, right? On the other hand, we want it to be as big as possible. But there is another thing to control it. The other thing controlling it is the window receive buffer. Okay, the receiver side has a receive buffer, and let's say imagine that we are having a first easy example here, 1,000 bytes on the network layer, pushing data to the transport layer, and the transport layer know that I only have 1,000 bytes. So what shall we do? Okay, now we actually having a producer-consumer problem. All right, the producer is the network layer. The other side send data in, and the network layer produce data to this buffer. And who is the consumer? Your application. Okay? So it depends on the consumption rates. If the arrival rate, now here what I say. If the arrival rate is stronger or bigger than the consumption rate, what will happen? Buffer will full. It must be full. Okay? So when it must be full, now we look at this problem in 2 ways. The first problem is, I don't care why the consumption rate is small. I don't care. Okay? I just care what is the mechanism in controlling this. How can I, let's imagine this is a simple producer-consumer problem back in the operating system course. The producer will eventually be blocked, right? The consumer is having a slow rate, and the high rate producer is being blocked. And when it's blocked, it's kind of a synchronization between the sending rates and the receiver rates. Now, how can I block the producer? Let's see. Okay, so very simple. Now, first of all, in a three-way handshake, we already advertised that our Windows is 1,000 bytes. And I say that the other side will respect my field here. Okay? But how can I keep telling the other side that I have fewer and fewer buffer, okay? So the way is very simple. When I have an inbound traffic, the incoming traffic of 500 bytes, I will consume my 500 space here. Now it depends on whether the application will take that 500 bytes or not. Let's imagine that I suspend the process. I suspend the application process. So there's no way to call the read system call and no way to pull data out of the kernel buffer. Okay, then I will, totally out of control, right? Because it's kernel stuff, the kernel will automatically send acknowledgement. Acknowledgement, remember? I send something to you, you send me acknowledgement. And acknowledgement also contains the Windows advertisement. The Windows advertisement is telling you that I have a fewer size. Don't push. Don't push more. Okay? Now, for the other end will respect this 500. With this 500. And let's say the other end is a very, how can I say? How can I describe? No, not brute force, okay? It's a very, how can I explain? Aggressive. Oh, right. Yeah, I found it right word. Okay. Aggressive. Okay. Let's imagine that the other side is very aggressive. Okay. It's pushing 500 again. It don't want to stop. Okay. Then the other side now will find that I receive an acknowledgement. The acknowledgement has some special meaning. It is zero window acknowledgement. Zero window. So what's the meaning of zero window? It means don't push. Don't push. Stop. Okay? When you stop, okay, you have to wait for the application to take that message. Okay? Now, but I don't want to explain to you on the application side. Let's imagine on the other end, I receive the zero window advertisement. So what will the other end will respond? The other end will stop sending any packet out. Will stop. Totally stop. Okay? Why? Because you tell me that you don't have any space now. Okay? So I shouldn't push any data out. Very natural. And this is the reason, and it is nearly the only reason, because nowadays the network is very fast, both ends are very fast. Okay? We don't have a problem on the medium is too slow. Let's imagine the medium are fast enough. Okay? So here is nearly the only reason that when I send data out, I call write system call and I get blocked. Right? When I get blocked, it means that I'm being forbidden to send anything, and because the other end don't let me to do it. Okay? So how can you produce this effects? Very simple. You use your assignment 1 application. Okay? You suspend the server. And use the client, I shouldn't say this. Okay, first, you tell the server and client to run, and the client try to upload a file, 2 GB. Okay, you choose 2 GB file. Once you press enter, we want to send, and immediately you suspend your server. Then you have this effect. Okay, you have this effect when you suspend the server. Okay? Then how about the receiver? The receiver, let's say I originally suspended, now I've continuous execution, okay? Now when it continues execution, it will start reading, okay? When it starts reading from the network, it will consume the data. Of course, it's in a FIFO manner, okay? But I have a drawing here, so I cannot show the FIFO manner here. So we take it in a FIFO manner, then I take 250 bytes. Now we have 250 bytes. Good. Tell the other side that I have 250 bytes holes here. Please consume it. Okay? So this is the way to resume the data transfer. Okay? So this is an advertisement mechanism and how to synchronize both end speed. Okay? So you will experience what? In a sender, you will experience periodic suspension of the sending, right? You want to send something, suddenly you find a suspend, not suspend, but the write call is being blocked periodically. Okay, sometimes you can push data, sometimes you get blocked. Okay, and in other side, because other side may be slow. Okay, so you have this problem. It's not just because of slow. Okay, so there's a window field. Not just because it is slow, but it's also because this write guy may be sending data in a too fast manner. Okay, so I will show you some very important thing. You can only understand it after you finish the exercise assignment 1. What is that? Okay, so I will go a bit faster to this table. So with this table, this experimental measurement that I use. Okay, I choose a longer path. Okay, I'm not doing in my own office land. Okay, when you go to my office, you know I have several hubs. Okay, and actually I have experimental land in my office, and this is one of my PC in my office, and I choose a longer path. I want to reach our department Linux 4 machines. Okay, and what I'm doing, my Linux, my Windows, not Windows, sorry, I use Linux. Okay, my Linux is using what we call I call it black hole server. Okay, what does it mean a black hole server? Whenever you send anything to me, I don't give response. Okay, just that means it's a one-way direction. And how about the Linux 4? I choose it to be client. Okay, now look at this matrix. So what is this matrix? I classify either the server or the client. They have 2 states. One state is the polite state. Okay, just like that when you look at some car advertisement, the car have a normal mode or sport mode. Okay, so normal mode, 4-byte reading. How about client normal mode? Also 4-byte reading. Then we measure the speed. Okay, how to measure the speed is very simple. Let's say I pump out 1 billion of bytes, okay, and I measure the time, how many time I need it. Okay, then 1 billion divided by the time needed, then we have the throughput. And the throughput is this. And what is my network? Okay, I measure the network using one very famous tools. So what is the famous tools we have? We call it iPerf. Do you know what is iPerf? No one heard of. Great. So that's why I can have a demonstration, okay? So let me connect to the department. Okay, good. So this department server, SSH, which machine you use most? Maybe Linux 1, huh? Okay, so there is a program called iPerf. I install in my, is it? Oh yeah, I install it should be in a spot. Okay, top one. CD iPerf. Let me try. I don't know what is a compilation. iPerf. Oh, actually I'm compiling Linux. Okay, iPerf. No source. Right. Okay. So this is a iPerf program. So I can also install it in my Mac. So my Mac also have iPerf program. So iPerf is a performance testing tools. You can set one guy as the client, another guy is the server. So let's imagine that I set the server on the Linux. So -s is the server. Okay. So it's waiting for something to happen. So I better detach this shell. Okay, so this is the server, and wow. So this is the client. I use my Mac to trigger the measurement. So the client, the host is Linux 1.csc.chk.ed.hk. Now go. It takes around 6 seconds. I guess it's maybe not 6 seconds, maybe faster. 3 seconds enough. Good. So it is not fast enough because first I go through Wi-Fi. This is a Wi-Fi connection, and the connection also go through our VPN. Okay, so it is kind of slow. But what if I do another crazy stuff? So the crazy stuff is I go out of Linux. Okay, I'm in my local machine, iPerf server. Okay, and then iPerf client is, 127.0.1. Guess what is the throughput? I guess it's a scale of 2-digit gigabit. I guess 2-digit gigabit. Wow. Yes, I win. 31.8 gigabit per second. Okay, so it's a local host communication. Now, I have measured the speed between these two hosts. Approximately, it is a 100 megabit Ethernet. 100 megabit Ethernet. Now look at my measurement. If they being polite, you will have a very slow network traffic. Do you know why? Natural, right? Is it natural to you? If both ends being polite, you have a 20 something megabit per second. Okay, I write my program by myself, so I guess the connection measurement is kind of okay. Now, how about aggressive server, hungry server, or I should say, what is the meaning of hungry server, and what is the meaning of 1448? Okay, what is the meaning of 1448? This data we will verify later by Patrick, but if you're impatient, I can calculate it to you. So, we have a 1,500 Ethernet packet width, okay? And what is the header length of a TCP header is 32 bytes. And we have extra 20 bytes of network header. So that means when using Ethernet, the width is 1,500. You decrement 20 bytes from the IP header, 32 bytes from the TCP header, then 1448 will be per packet maximum data size. Okay, so I use this number and fit it into the read system call when I behave to be a hungry server. If I behave to be an aggressive client, I will also use this 1448. What is the meaning? The meaning is I want to push the whole network to the limit. Okay? Understand what is my purpose? Now look at the data here, the matrix here. These three numbers are not performing okay. This is the best. Why is this the best? Very simple. You keep on pushing the network to the limit. You keep on pushing data in. And while you're pushing data in, you are nearly always boosting the buffer, receive buffer to the limit, very close to the upper limit. Okay? And while on the receiver end, you are nearly always take out most of the data as you wish to take. Okay? And that means this is this diagram. Okay, I should use this diagram better. The producer and the consumer one guy always push the buffer to be full, and one guy is always also empty the buffer. So it is the fastest way, okay? But you can argue, hey, this is a polite server and a polite client, they always produce the same effect, right? You try to push as few data as possible. Yes, you take as few as data as possible, pushing 4 bytes, take 4 bytes. You still don't push the buffer to be a full state. Okay? Why is it compared to it nearly losing four times of the throughput? Do you know why? Why it cannot have because here I guess it won't have a zero window acknowledgement problem. Okay, there's no zero window acknowledgement. That means that buffer cannot be full. Here is also the same case. The buffer cannot be full. And the same reason applies to this here, to this side. This side is a hungry server. The server always wants to take data out. Okay? Keep on reading as much as possible. But the other side sending very slow. Okay? Can anybody explain to me why? Don't know. Anybody want to try? Why?
I can think of two reasons. The first one is that the read-write system call there are overhead in the read-write system call, therefore the processing rate is lower in the application layer. Mm-hmm. And the second one is that when you send small packets, you have an overhead in the
So I kind of accept the first answer, but the second answer, I tell you why I accept. The first answer is correct by him. Okay, very good. What is the reason? The reason is basically the read-write system call has its overhead. As if in 1 second, you have limited the number of time of read-write system call, right? You have overhead. The overhead cannot be avoided. Okay, so the number of times of system call is actually being limited. Let's say you can only call at most 100 system call, 100 read system call in 1 second. Now within that 100 call, you don't try to maximize the data you want to send. It's your problem, right? If I want to maximize the data I want to send, I use an aggressive mode. Then I can get the most from the network. And your second answer is not that good because the network header, how can I explain? The network header is also appear in the aggressive mode.
But you have small packet. If you have small packets, and the header takes most of the bandwidth.
Right.
But do you mean you will have?
I mean, the first effect is a dominating effect. Okay. Yeah. Okay. So this is the reason. Okay. And now you understand that in implementing your assignment 1, okay, because our assignment 1 don't measure any throughput, okay, let me do a first easy survey here. The survey is your read-write call, okay, what is your buffer size? Still remember, what is the buffer size? Who has a buffer size more than 500 bytes? Yo, you, okay, what is the size? 100, okay? 100, I guess still okay. Still can reach around 15 megabytes per second. I think megabit per second. Okay. How many of you is below 1,000? More than 1,000? Only you? So how about others? And mmap is you still need to call the read. Okay. Yeah. Then it's no effect. Okay, because I already push it to the limit for Ethernet. Okay, unless you are not using Ethernet, then it's another problem. Okay, so it means that this 1448 is a magic number. Okay, this magic number, as long as you're using Ethernet, we are already pushing the whole trunk of data, plug it into the Ethernet, and there is no gap in that Ethernet packet. Okay, and we fill all the gaps. So basically, this is the best number that I can do under this best number combination. Why I cannot get 100 megabytes per second? Megabits. Why I always say megabyte. 100 megabits per second. Why I cannot get it? Do I have any calculation error? No, I don't have any calculation error. So let's try, huh? I don't know whether the department has do any upgrades. Okay. So I have to first go to my Linux. Okay. I just upgrade my Linux. Okay, from changing the 100 megabit per bit never cut to 1G. Okay, so I don't know what will happen. Okay. So yperf. Let's say I'm the server. Okay, this is my Linux. Oh yeah, I didn't install yperf. Oh shoot. Okay, then I go to my Mac machine. Okay, this is my Mac. Okay, yperf. Let's say this is my server. Then I SSH to which Linux do you think is sucks enough? Which one? Linux 1. Linux 1 is bad. Okay, yperf client. I go to reach my Mac machines. What? Oh, yperf. Okay. I don't know what will happen. Can I have something good or bad? Oh, I changed I upgrade my computer, so it's become something like this. Okay. Yeah. It showed that my computer worked perfectly with my Linux. Okay. Our Linux machine is 1 gigabit per second Ethernet. I can still keep this question valid. Why I cannot get 1,000? as in my experiment. My experiment is using a cheap hub, another hub. Actually, it's just a network switch. Okay, a very bad switch. Okay, the Linux size on the Linux is measured 912. My Mac machine measured 910. Just some calculation, a timing error, I would say. So it's just timing error, no problem. Okay, but why can I get 1,000 or even close to 1,000? Yeah, you already answered the answers. Okay, so how about others? Do you know why? I can push data as much as possible now. I imagine that this iPerf is using the way that I implement the black hole thing, the measurements, so on and so forth. Now I cannot get close to 1,000. Not even 980 something, but 910. Okay, and in my experiment is not 100, but 93 something. Not even close. Why is that? Any idea? No? No idea? Still remember what I just calculate, this 1448. Okay? I basically calculate the throughput using this application data transfer. But more than application, we also transfer between the two hosts the header of TCP and the header of IP. Okay? So, although we every time transfer so many data, okay, it's actually of that percentage. Okay? By calculating the useful percentage, we can only at most get 96. Okay? So how about the time that I need to take in order to wait for acknowledgement? Right? I didn't take account into it. Okay? I may also need other times in doing the system call, reading, writing. Okay? So the network overhead together with the host overhead, we cannot get 100 or 1,000. Okay? And the calculation for the network size like this, and some others that I cannot quantitatively tell you, I can only tell you the reason behind. Okay? So this is a very interesting experiment. Okay? I really love to have this data to share with you because it's to teach you how to write a good client and a good server in your assignment 1. And as well as other applications later on when you're doing. Okay, so another similar experiment, I write a simple program here. I call it a packet alternation program. This program later on in assignment 2 you will be writing as well. Okay, what is the meaning? Okay, I can install run a program as a root, as administrator on my PC, and whenever there is a packet arrive, or sending out, I change it. Okay? So what is the thing that I change? I change the window. Okay? I disregard the three-way handshake. Okay? I disregard what the three-way handshake is saying. Okay? The data is pushing from the client to the server, and whenever the server tries to reply to the client, I alter it. Okay? I change it. The first time I tell the other side that the server, after it sends acknowledgement, I tell him I only have 1,600 bytes on my buffer. Okay? And if I do it every time, look at the throughput. Wow. Interesting. Slightly better than modem. Here, if I double the window size, okay, I can have a slight improvement. Okay, and later on, I can explain to you why we have a nonlinear growth. Okay, later on we will understand what is the nonlinear growth part here. Okay, so any question you want to ask in this part? Okay, and then if you don't have any question, we'll jump into another part. Before I jump to another part, I want to have a very short summary. The summary is that now you kind of understand. When you start your download, okay, I don't know what is your internet age, okay, how old you are on internet, I don't know, okay. But when I first entered the internet, okay, I experienced something interesting. Now it's totally another story. at my age, okay, while at your age, not at my age now, at your age, during 1990 something, we have such kind of growth of the download rate when I want to download something. Now it's not the case, right? What is the current experience is starting from zero, exponentially growth, and then suddenly drop, and then steady. Is it your experience, right? You start with zero, and then suddenly tell you that 10K, and then suddenly 100Ks, and then suddenly tell you 600Ks, and then suddenly drop to 400Ks, and then keep steady, right? In a time that during my time in 1990 something, I have this experience: linear growth, and then suddenly drop, and then like this. Okay. Now, what is this point? This point is actually we can explain by some of the effects. What is the effect? We call it the increasing advertisement window. So what is the meaning of increasing advertisement window? One point that I didn't explain to you guys is here. Something that I cannot teach, even I teach the elite class of the 4430. What is that? Because it's something that is not even documented. I look at the kernel code, source code, I kind of understand what it's doing, but there's no documents. Okay, it's only have this the best thing I can have. That's called TCP auto tuning. TCP has some I would say that try to give you a good experience. If we find that if both ends, okay, one guy is aggressive sending things, one guy aggressively reading things, the TCP flow will start to sense that, maybe both guys, one is too hungry, one is too aggressive, maybe I expand the buffer. Okay, maybe I expand the buffer. So what is the meaning of expand the buffer? Okay, so here, this field. This field is not fixed. It's not always saying that I have 1,000 bytes. It can grow, okay? But we cannot document this. Even in textbook, in a wiki, okay, they don't tell you exactly what is going on, okay? We can only understand by looking at a Wireshark capture, okay? Or you want to understand this, you can go to my office. I can share with you what I find during the preparation of the elite class of the 4430. Basically, I find a linear growth. Okay? But now your experience is not linear growth, okay? Because there is another thing that controlling the TCP flow. We call it a congestion window or congestion control, okay? By looking at the congestion control, later on we will understand why it behaves in another way, okay?